This circuit I've split up into separate chunks to try and describe it for you. So the first part I'm looking at is the voltage divider with 4 fixed resistors, providing 3 fixed references. It doesn't ask you to calculate them, but by calculating them, you can put a number on it, which will help you analyse what's actually happening. So some people are still struggling to calculate voltages out. It has to be the resistor 2, so the voltage dropped across the 100 ohm resistor, for example, divided by the resistance total. So that's all of those resistors added together. And you can see I've done the same there. 1000 ohms this time, that's those 2 resistors, so that's the voltage here, divided by, again, the resistance total. So some people are still making careless mistakes with calculating voltages out of a voltage divider. This box down here is the first part of my description, so I'm simply describing that the potential divider made up of the fixed resistor produces different fixed values of voltage at the inverting terminals or inverting inputs of each op-amp. The voltage values at the inverting inputs increase from op-amp 1 to op-amp 2. I've then moved on to look at the other voltage divider, which is made up of a variable resistor and an LDR. Now, you don't need to be able to read the numbers, but we can see that from dark to light, the resistance of the LDR goes from high down to low. So therefore, if we have a high resistance going to a low resistance on the top half, that means that the voltage out here is going to increase from low to high. Okay, so the voltage here is going to increase. So again, my description, the potential divider including the LDR produces a voltage that increases as light level increase. Because of the resistance of the sensor reduces, the variable resistor enables the voltage at the non-inverting terminal or input to be adjusted at a particular light level. So this part here, the question doesn't ask us for it, but I think it's quite useful to create this table. So this is the voltages that would be coming in from the first voltage divider. I know that this is 0.049, 0.49 and 4.95 volts coming out here. So I've deliberately picked a number less than 0.049. I've picked a number that's between 0.049 and 0.49. And it's then getting brighter again, a number that's higher than 0.49 but not quite at 4.95, and then one that is above 4.95. I can then analyse each individual op-amp, op-amp 1, what's happening? Well, the voltage that's being applied here is going to be less than the 0.049. So therefore I'm getting a low signal out. That low signal out means that output Z is going to be off. Okay, these are also giving off signals. So the first line is all the op-amps are off and Y and Z are both off. As it starts to get lighter, I'm now getting 0.3 volts from the first voltage divider. So 0.3 volts, that means that this voltage at the non-inverting input is now greater. So this first op-amp, op-amp 1, is now on. So I've got an on signal, which is getting combined with an off through the NOT gate, becomes an on signal. Suddenly the AND gate will think, well, that's a 1 out, so output Z is on all by itself. As it gets lighter again, I've now got 1 volt coming out here, which is going to be greater than voltage reference 1 and voltage reference 2. So both this op-amp and op-amp 1 and op-amp 2 are both going to be on. If both are on, then we've got Y on by itself. That's nice and easy. That on signal through the NOT gate becomes a 0. On signal, but with a 0 and a 1, that's an AND gate, so that's a 0. So Z is going to be off. So here we've got Z off, but Y on by itself. Then, as the light gets brighter again, 5 volts is greater than all the 3 reference voltages, which means all 3 op-amps are on. The digital signals coming out means that I've got Z is on, I've got Y on. Okay, so the table there is not asked for, but does help with your description. This next slide, I have tried to put my description now into words, so telling a story, just like I was a minute ago with the table. You're starting at low light levels. The output of all 3 comparators are close to 0 volts. Output Y and Z are both low or off. As the light increases sufficiently, the voltage at the non-inverting input of the comparator increases above the value set at the inverting terminal, comparator 1, and then it tells the story, and it goes on, okay? Second part of the question asked us to determine the light level at which output of op-amp 2 switches from 0 to 5 volts. Show you're working. So this voltage here, voltage reference 2, that is the trigger point for op-amp 2. So I've been able to calculate that earlier on, 0.49, but the comparator is comparing it against the voltage at this point here from the first voltage divider. So we can assume that the switch on, switch off point for that comparator means that 0.49 volts is also dropped across the variable resistor. It tells me in the question that that's set to 1100 ohms or 1.1k. And so I can use my knowledge of electronics. That's going to be 4.51 volts dropped across the top because they have to add up to 5 volts. Then I can simply use the formula V1 over V2 is equal to R1 over R2. Working out the R1 equals, that's the resistance of the LDR, works out to be 10k, 10,000 ohms. And so using my graph, I can establish that that's about 9 or 10 watts.